Hello, I'm Dr. N. Hulle. In this video, we'll try to understand the problems on transient response of the RL series circuit. To begin with this problem, for the circuit shown below, which is in position 1, that is this, for a long time, that is the steady state was reached, and the switch is shifted to the position 2, which is this. At t is equal to 0, find the following. First is expression for the current for t is greater than 0. Draw the variation of I of t for t greater than 0 and voltage across the resistor and inductor. We are interested in these calculations. Now look at what is the difference between this problem and the problems which I discussed in the previous video. In this case, we have the source before switching as well as we have the source after switching. In this case, depending on the value of the source before switching and after switching, it behaves similar to the source driven or source free RL series circuit. In this case, applied voltage before switching is a 40 volt and applied voltage after switching is 10 volt. Means voltage applied after switching is less than as that of the voltage before switching. Means in this case, the circuit behaves similar to the source free circuit with certain conditions. Those I will discuss with the variations of IFT for t greater than 0. Now here, as we have the general procedure, we will follow that. We will analyze the circuit before switching and we will analyze the circuit after switching. To begin with, first part is circuit for t less than 0. That is, we are analyzing the circuit before switching. In this case, applied voltage is the 40 volt because this is the circuit. This is 40 volt. This switch was in the position 1, which is shown here. This 40 ohm resistance is as it is. This is 20 millihenry and this should be replaced by the short circuit because in the final condition, inductor acts as a short circuit. Now this is the circuit for t less than 0. We are calculating the current at this instant, which is I of 0 minus is equal to I of 0 plus, which is equal to 40 divided by 40 because 40 is the applied voltage, 40 is the resistance, which is equal to 1 ampere. Now this 1 ampere is the current before switching. Now here in this case, we will try to understand the second part, which is circuit for t greater than 0. In this case, the source-driven circuit behaves similar to the source-driven RL series circuit with initial condition, and initial condition we have the 1 ampere. Circuit for t greater than 0, which I have drawn here, the switch was in the position 2 and in that case this source was disconnected from the circuit. It's only this part of the circuit will remain, which I have tried to show here. This is 40 ohm, this is 20 millihenries, and it is the 10 volt source is existing after switching. Now here we will try to find out its expression for the current. The first part is the expression for current for t is greater than 0. Expression for the current for source driven RL series circuit with initial condition, the general expression is I of t is equal to Im minus in bracket Im minus I naught into e raised to power minus t by tau, where Im is the current after switching, this Im is a current after switching, this I naught is a current before switching, e raised to power minus t by tau, tau is the time constant after switching. Now here in this case, first we will try to find out all these values. First is the I naught. I naught already we have calculated, which is the current before switching, that is initial condition of the current, which is 1 ampere. Now we will find out the maximum value of the current that can be possible after switching, which is when this inductor will become 0. In that case, the maximum value is possible, which is nothing but Im is equal to 10 divided by 40. That is 10 divided by 40 is the current that can have the maximum current flowing through the circuit, which is the 0.25 amperes after switching. Now time constant is L upon R, that is 20 into 10 raised to minus 3, which is 20 millihenries, divided by its resistance is 40, means it is 0.5 into 10 raised to minus 3 second is the time constant. Now I will substitute the values. This Im is a 0.25 minus this 0.25 is this Im again, and this I naught is 1 ampere into e raised to power of minus t by tau, and the value of the tau is nothing but 0.5 into 10 raised to minus 3. We will simplify this expression. Now here in this case, this I naught is a greater. That's why here the subtraction of this result is a negative value. This minus into minus, this value will be plus. Means it is 0.25. This subtraction is a 0.75 into e raised to power of minus t by tau, and tau is a 0.5 into 10 raised to power of minus 3. Now here in this case, I naught is greater than Im. So the resultant equation is similar to the discharging of the current, because the applied voltage before switching is a higher value than applied voltage after switching. That's why its behavior is similar to that, which I will discuss in the next slide. Now here in this case, we are trying to understand the variation of I of t for t greater than 0. This is the circuit which I was considered in this particular case. The expression already we have calculated, that is I of t is equal to 0.25 plus 0.75 into e raised to power of minus t by tau, and tau is the 0.5 into 10 raised to power of minus 3. Now we are calculating I of t at t is equal to 0 and t is equal to infinity for plotting the value or drawing its variation for I of t for t greater than 0. At t is equal to 0, thus t is 0 means it will become e raised to power of 0. E raised to power of 0 is 1. 1 into 0.75 is a 0.75 plus this 0.25. Means here the total value is 0.25 plus 0.75 is nothing but 1 ampere is a current at t is equal to 0. Means at this instant, that is t is equal to 0, its current is 1 ampere. Similarly, we are trying to find out the value of the current at t is equal to infinity. At t is equal to infinity, it will become e raised to power of minus infinity. Now here e raised to power of minus infinity is 0. 0 into anything will be 0. This resultant value is 0.25. Means it is 0.25. Means at t is equal to infinity, this is time axis, this is t is equal to 0, and this will be the t equal to infinity. And at the t is equal to infinity, the current in the circuit is 0.25 amperes, which I have tried to show here. This is the initial current and this is the final current, and it is discharging. Now here discharging to its value, and its value is 0.25, and the expression is I of t is equal to 0.25 plus 0.75 into e raised to power of minus t by tau. Now here, due to the available initial condition in the circuit, the current is not going to decrease completely, because in the second case also there is existence of the applied voltage, and due to this applied voltage, the charge existing on this is the 0.25 amperes. And this is the variation of this case, and the circuit is behaving similar to the source free RL series circuit with some conditions. Now here we will try to find out its expression for voltage across inductor. Now here better to use, because many times we have the different equations for the source driven circuit and source free circuit then with initial condition. That's why better to use only one expression, and that equation is nothing but VL is equal to L into di by dt. Here L is the inductor, which is 20 into 10 raised to the power of minus 3. Differentiation with respect to T of its current is 0.25 plus 0.75 into e raised to the power of minus t by tau, where the tau is 0.5 into 10 raised to the power of minus 3. We will simplify this equation. Now here inductor is the same as it is. The differentiation of this constant term is 0. The differentiation of this term is 0.75 is a constant. The differentiation of e raised to the power of minus t by tau is minus 1 upon tau into e raised to the power of minus t by tau. If we are simplifying this expression, it will be its value is VL is equal to minus 30 into e raised to the power of minus t by 0.5 into 10 raised to the power of minus 3. This minus sign indicates that current in the circuit before switching is higher than after switching. That's why DI is a negative, and it is similar to the discharging case, because applied voltage before switching is 40 volt and applied voltage after switching is the 10 volt. That's why its value is something like that. Now here expression for voltage across resistor, which is again R into I of t, there is 40 into this expression for the current, that is 0.25 plus 0.75 into e raised to the power of minus t by tau. If we are simplifying this, 40 into 0.25 is a 10, 40 into 0.75 is a 30, means VR is a 10 plus 30 into e raised to the power of minus t by 0.5 into 10 raised to the power of minus 3. This is the solution for this particular problem. Now I will consider the similar case or similar problem, but with higher voltage after switching. Now here in this case, this is the next problem. In this case, we are interested in the calculation of the expression for the current for t greater than 0, variation of I of t for t greater than 0, voltage across a resistor and voltage across inductor for this given circuit. What is the difference? Difference is that applied voltage before switching is a 40 and applied voltage after switching is 150 volt. And in this case, we'll try to understand its behavior. This problem is very same as the previous one. Only difference is that in this particular case, in place of this voltage as a 10 volt, we have considered this voltage as a 150 volt. Now here we will analyze the circuit for t less than 0. In this particular case, we will calculate its current, which is nothing but that is I of 0 minus is equal to I of 0 plus, which is equal to 40 by 40, which is 1 ampere. Similarly, we will try to draw the circuit for t greater than 0. This is a source driven RL series circuit with initial condition. Here from this case, if we are shifting the switch in the position number 2, in that case this part of the circuit will be the active, that is 150 is the applied voltage. Here the 40 ohm is the resistance and 20 millihenries is its inductance in this particular case. And here we will find out the expression for current for the t greater than 0. Again, the expression for this case will be the same as I of t is equal to Im minus I naught into e raised to power of minus t by tau, where Im is a current after switching, this Im is a current after switching, this I naught is a current before switching, and this t is a tau. Now here in this case also I naught is 1 ampere. Here Im is 150 upon 40, because 150 upon 40 will be the maximum current, which is 3.75 amperes. Tau is equal to L upon R. L is the inductor, which is 20 into 10 to the power of minus 3 divided by 40. Its value is 0.5 into 10 to the power of minus 3 second. Now here its expression for I of t will become I of t is equal to Im, which is 3.75, minus this value is Im again, which is 3.75, minus I naught, which is 1, into e raised to the power of minus t by tau, and the tau is 0.5 into 10 to the power of minus 3. Now in this case, this subtraction is a positive value, 3.75 minus 1, because in this case Im is greater than I naught, and this subtraction will be the minus 2.75, that is 3.75 minus 2.75 into e raised to the power of minus t by 0.5 into 10 to the power of minus 3. Now here in this case Im is greater than I naught, so resultant equation is similar to the charging of the current, that is source driven case, which I will discuss maybe in the next slide. Now here in this case we are drawing the variation for I of t for t greater than 0. This is the given circuit. Here expression for the current is I of t is equal to 3.75 minus 2.75 into e raised to the power of minus t by 0.5 into 10 to the power of minus 3. We will calculate I of t at t is equal to 0 and at t is equal to infinity. If we are finding its value at t is equal to 0, its value will become e raised to the power of 0 is 1 into 2.75 is 2.75, means, and final solution will be 3.75 minus 2.75 will be, it is 1 ampere. 1 ampere is the current at t is equal to 0. The current at t is equal to 0 is this 1 ampere. At t is equal to infinity, I of t is, we are finding e raised to the power of minus infinity. This minus infinity, this term will be the 0, 0 into anything will be 0. This resultant value is 3.75 amperes, which is the 3.75 at t is equal to infinity. This is the maximum current. This is the initial current. This is the final current. Is here the current is exponentially increasing, shown by this particular graph, which is I of t is equal to 3.75 minus 2.75 into e raised to the power of minus 0.5 into 10 raised to the power of minus 3, and this case is very same as the case of a source driven RL series circuit. Finally, we are interested in the expression for the voltage across the inductor. I will use this general formula, that is VL is equal to L into di by dt. We will substitute the value of the L and this I of t. We will find out its differentiation. We will use the simple steps, and its voltage across the inductor will be 110 into e raised to the power of minus t divided by 0.5 into 10 raised to the power of minus 3. This is the expression. Similarly, the expression for the voltage across resistor is VR is equal to R into I of t. Resistance value is 40, and this I of t is 3.75 minus 2.75 into e raised to the power of minus t divided by 0.5 into 10 raised to the power of minus 3. And finally, we will have the final equation, that is voltage across resistance is nothing but that is 150 minus 110 into e raised to the power of minus t by 0.5 into 10 raised to the power of minus 3. This always for the calculation of the voltage across inductor, we will use the formula VL is equal to L into di by dt, and for the calculation of the voltage across resistor, we will use the formula R into I of t. Thank you for watching this particular video. That's all.